Okay, everything is working, so we can start our lecture. And at the previous lecture, we discussed some of the implications of symmetry for the energy spectrum of a quantum mechanical system. As a general principle, we formulated the following slogan: the bigger the symmetry of the Hamiltonian, the more degenerate its energy spectrum. And conversely, small perturbations may break some of the symmetries of the Hamiltonian and hence diminish degeneracy or even complete remove it. Let's now look at some examples illustrating this general principle. Consider first a charged particle moving in a central force potential. So we have particle of mass m and charge E moving in central force potential, which is a function of the length of its radius vector. Okay. And we know that the stationary states of such a particle can be conveniently described in terms of the three quantum numbers n, m, and l, where n is a principal quantum number, and Lm. L is the orbital quantum number or azimuthal quantum number, and M is the magnetic quantum number. And we can use also the first two quantum numbers, N and L, to tag the energy levels of the particle. So energy levels are labeled by N and L. As a result, the energy spectrum appears to be degenerate with respect to the magnetic number, right? So we have for M, for L, different from 0, the energy level is degenerate, and multiplicity of each level degenerates to L plus 1. Now let us, of course, this is well known, the so-called normal degeneracy related to the spherical symmetry of the problem. Normal degeneracy, which is caused by the spherical symmetry, that isotropy of physical space that is absent of a preferred direction in space. Now let us switch on an external uniform magnetic field H. Okay? As we know, in the presence of an external magnetic field, degenerate energy level splits, right? And instead of one degenerate energy level, we get a bunch of to L plus 1 close energy levels. A bunch of energy levels to L plus 1 energy levels. Okay, and this splitting is known as a Zeeman effect. Right? Zeeman effect. Zeeman effect. So we have several energy levels which now depend on the magnetic number. where M runs from minus L to L. So in total we have 2 elements, 1 energy levels. And the physical interpretation of such a splitting is, of course, the violation of rotational symmetry of the system. For weak magnetic field, the total Hamiltonian of the particle moving in response to the external central force potential looks as follows. H is given by p squared over 2m plus v of x, absolute value of x, minus e over 2mc angular momentum operator in a product scale product with H, external magnetic field. Okay, so since the magnetic field is assumed to be weak, we ignore all terms proportional to the all terms quadratic in H, right? Adding the last term, that is switching on external magnetic field, we break the rotational symmetry, SO3 symmetry, of the initial Hamiltonian to axial symmetry. We diminish the symmetry SO2. This is the axial symmetry because the total Hamiltonian is still invariant under rotations about the vector H. Under rotations about the vector H. But notice that the group SO2 is commutative, and hence all its complex irreducible representations are one-dimensional. It has no multidimensional, high-dimensional representation, and this implies immediately the complete splitting of the degenerate energy spectrum, because the symmetry group is abelian or commutative. Okay, so far so good. Let's now place our charged particle into an external electric field instead of a magnetic one. So again, we consider a central force potential, charged particle, but now we turn on external uniform electric field, E, right? Again, the presence of an external vector field violates the isotropy of space and forces degenerate energy levels to split. So again, instead of a degenerate energy level E and L, we get a bunch of closed levels. And this splitting is known as a Stark effect, right? Stark effect. But contrary to the Zeeman effect, the Stark splitting is not complete. There remains a twofold degeneracy with respect to the sign of the magnetic number. That is E n L minus M is equal to E n L M, where M runs from minus L to L. Okay, what's the matter? in both the cases, we break the spherical symmetry of the problem, to the axial symmetry. But for Zeeman effect, the splitting is complete, and for the Staff effect, it is only partial. Why? What is the difference between the vectors H and E?
Maybe is for interaction because our particle is charged.
Yeah, this is due to interaction, of course. But how we can explain? Can you explain this phenomenon from the viewpoint of symmetry? Yeah, hidden symmetry. Yeah? Okay. Actually, you're right. As I mentioned above, the presence of residual degeneracy indicates some extra symmetry or hidden symmetry of the Hamiltonian. I mean, extra symmetry in addition to the axial symmetry, rotational symmetry about given axis. Let us take a closer look at the perturbations of the energies that are caused by the external electric and magnetic fields. So what we have? For magnetic field, we have this term that is E over 2mc x1 p2 minus x2 p1 h, and for the electric field I have this operator x3 e. Here both the vectors h and e points at the direction of the z axis. So we align the coordinate system in such a way that both the vectors are along the z axis. And as I seen, the operator V2 corresponding to the electric interaction, it is invariant under space reflections. I mean reflections in the plane that are with respect to any plane passing through the vector E. So let me draw this coordinate axis x1, x2, and x3, and let's consider a plane passing through the axis x3, the z axis. So in particular, we can consider the following reflections when x1 goes to minus x1, x2 to x2, and x3 to x3. So our plane just the coordinate plane corresponding to x3 and x2. So we put here a mirror and get the reflection with respect to this mirror. And it is clear that the operator V2 being independent of x1, yeah, it is invariant under this transformation, discrete transformation. So V2 goes to V2. And what about V1? Is it invariant or not? Well, when we change sign of x1, the first term acquires minus sign. And the same is true for the second term because of P1. what is P1? P1 is given by IH d over dx1. So when we change the sign of x1, P1 goes to P minus P1. So under this reflection, V1, the operator V1 is not invariant. It's not invariant. It changes its sign. So we thus conclude that the symmetry group of the Stark effect, or symmetry group of the electric interaction, can be extended by the reflections in space, right? So we can extend it from SO3 to a bigger group, O3, the full group of orthogonal transformations in space, in three-dimensional space. I'm sorry, not. We are talking about rotations, about the z-axis. So we extend SO2 to the orthogonal transformation of two-dimensional plane, right? O2. And it is significant that the full orthogonal group O2 is not commutative, because in general, reflections do not commute with rotations.
Can I ask a question? Now we try to find the group of symmetry from symmetry of problems.
Yeah, we consider a particular Hamiltonian with particular type of interaction, and we see that actually its symmetry group can be extended from SO2 to O2. And the group O2, as I have said, is non-commutative. What does it mean? It means that this group may have some higher dimensional irreducible representations. Actually, only two-dimensional representations. Only two-dimensional representation. And this is the reason why the removal of degeneracy in the case of the Stark effect is not complete. Because here we can consider the pair of states, here the pairs of states are with opposite magnetic numbers, and the various linear combinations of these states span two-dimensional complex space and a two-dimensional complex space of an irreducible representation of the orthogonal group O2, and all these vectors are in space, being physically equivalent, they have the same energy, and this explains why there is a twofold degeneracy of the energy spectrum in the case of the Stark effect. Any questions?
Yes.
Please.
The origin of the Stark effect is from anti-symmetry of X1.
Not anti-symmetry of X1. We speak here about some space reflections. So we can take any plane passing through the vertical axis, any plane. Okay, and a reflection in this plane then is a symmetry of our potential. So these reflections, they affect only coordinates x2 and x1, right? But these coordinates do not contribute to the expression of the potential V2, right? And as we know, such reflections, any such reflection is also the symmetry of our central force potential. So it's the same central force potential, which is invariant, and any reflection and those which live invariant are the interaction with external electric field are the symmetry of the total Hamiltonian, and we see that the symmetry group is actually bigger than the axial group SO2. It can be extended to the full orthogonal group, which is non-commutative. So we have some two-dimensional irreducible representations that are spanned by the pair of vectors with opposite magnetic numbers. It is the space of C2 of a reducible representation of O2. As a last example, let us consider the phenomenon of accidental degeneracy, of the hydrogen atom, Put it as then shell entry hydrogen. Of the hydrogen atom. As you know, for Coulomb potential, in addition to the normal degeneracy related to the rotational symmetry, to the spherical symmetry that we have just discussed, there is an incidental degeneracy with respect to the orbital number L, with respect to the orbital number. And the examples above suggest that this degeneracy must be maybe a consequence of some hidden symmetry of the Hamiltonian describing the hydrogen atom. Such a hidden symmetry does really exist and is generated by the Runge length vector. Runge length vector, which we denote usually by A. As we know, to each of the three components of this vector, we can define a Hermitian operator, x1, x2, x3, Hermitian operator which commutes with the Hamiltonian. So all these three components are constants of motion, integrals of motion. Okay, now according to the quantum version of the Noether's theorem that we had discussed at the previous lecture, these operators generate one-parameter groups of symmetries of the Hamiltonian, right? And it should be noted, however, that the corresponding symmetries are non-geometric, because in the coordinate representations, these operators are A1, A2, A3 are the second order differential operators. So they generate non-geometric symmetries which are not obvious. In contrast, for example, to the components of the angular momentum operators, which are differential operators of first order. Anyway, it can be shown that taken together, these operators Mi and Aj, they generate a 6-parameter Lie group, which is isomorphic to the group SO4. Generate a group SO4. That is rotation group of four-dimensional Euclidean space. It's rather interesting because we started with some physical problem in three-dimensional physical space, hydrogen atom, and we found that its symmetries of this problem, three-dimensional physical problem, is actually can be described in terms of rotations in some four-dimensional space. This space with one additional dimension. And then each eigenspace with definite energy, let me denote it by Hn, carries an irreducible representation of the group SO4 of dimension n squared. So dimension is equal to n squared. That's the multiplicity of each energy level of the hydrogen atom. Yeah? The extent of the degeneracy is n squared multiplicity. And each of this space transforms irreducibly under the action of the group SO4. However, when we restrict this group SO4 onto a subgroup SO3 generated by the components of the angular momentum, this representation, irreducible representation, becomes reducible. It decomposes into the direct sum of irreducible representation of SO3 of the rotation. So we get a direct sum of invariant subspaces for the rotation group, which are labeled by the value of the angular momentum. L runs from 0 to n minus 1. And as we know, each invariant subspace with respect to the rotation group has dimension to L plus 1. And summing up all these dimensions, okay, of course we get the dimension of the space H sub n, that is n squared. Notice, since there are components of the Runge length vector do not commute with components of the angular momentum, for J is not equal to I. Just a moment. When these operators A act in the Hilbert space Hn, in subspace Hn, they mix the vector from different invariant subspaces for the operators M. So the representation of SO4, which is generated by both M and A, appears to be irreducible. Okay, question?
Yes. If we have some group can form the algebra.
Group from the algebra? What does it mean?
If, for example, if we have a Lie group, we can construct the Lie algebra.
Okay. For the groups we have the algebras.
And it's how we can apply what we have constructed the algebra in symmetries of some problem.
Well, in terms of the serial, in terms of the serial of Lie algebras, our generators M and H are the element of the Lie algebra, which is behind the corresponding Lie group. So each Lie group is generated by some Lie algebra, but we don't use this terminology of the serial of Lie algebras in our discussion. This will be the content of the next semester on group theory, where we will discuss the algebras and their relationship with Lie groups. But for now, the generators, for us, the generators of some continuous symmetries are just integrals of motion of the problem under consideration. So we have some integrals of motion, and according to the quantum counterpart of the Noether theorem, we can generate the corresponding symmetries, and we ask what we can infer from these symmetries in terms of the energy spectrum. And we see that the hidden symmetry, why it is hidden? Because it is non-geometric, right? It is non-geometric. It is symmetry in some four-dimensional, implicit four-dimensional space. But this is a symmetry of our problem, and the presence of this symmetry, hidden symmetry, explains this phenomenon of accidental degeneracy of the hydrogen atom. Okay, more questions? Okay, then let's move ahead. The next question we will consider is called group theory and selection rules. The next section is called group theory and selection rules. Group theory and selection rules. The group theoretic methods can also be applied, also provide a uniform approach to the derivation of selection rules for the matrix operators of for the matrix elements of various operators. So that we have given some group G that acts by unitary operators U in some Hilbert space of some quantum mechanical system, and then we say that a set of operators acting in the same Hilbert space, H, set of operators, let's consider finite sets, set of operators, form a tensor operator, of the group G if they satisfy the following relations: U dagger So we apply unitary transformations from our group G to our operators, to our set of operators, and we again get some linear combinations of the same operators, from the same set. If this happens, we say that this set of operators as A form a tensor operator. Tensor because we have some index A. And now it is easy to see that these coefficients of linear combinations T, they form actually a square matrix, and these matrices for different group elements, these matrices define a representation of the group J. So representation of the group G, of the group G. Actually, n-dimensional representation, because we speak about the set of n operators as n-dimensional representation of group G. And this tensor operator as A is called irreducible if the corresponding representation T is an irreducible representation. Irreducible if and only if T of G is an irreducible representation of the group G. Is it clear? I mean definition. Okay, let us take the rotation group SO3 as an example. SO3 group. So J is equal to SO3. Okay, we can think about this group as a symmetry group of a particle moving in the central force potential, for example. And as irreducible tensor operators for the group SO3, we can consider the position coordinates, operators corresponding to the position coordinates, the conjugate momenta, the components of the angular momentum. All these operators all these sets of operators are reducible tensor operators with respect to the SO3 that transform according to their vector or fundamental representation of the group SO3. Let us check. For example, let's take the position coordinates. So we take the operators xi and conjugate them by the unitary transform corresponding to the space rotations. U dagger J, U, J. And to make this computation, it is convenient to apply this operator to some test wave function psi of x, because we know how these operators U act in the coordinate representation. So we have U dagger J. Now operator U being geometric acts from psi through its augment x, just rotating the radius vector x. And then we apply operator x, which is multiplication operator. So we get x I psi R to R of j to the minus 1 power x. Okay, do you agree? Now we continue. Again, we apply the adjoint operator, conjugate operator. But our representation is unitary, so this corresponds to the action by the inverse, rotation inverse element J. Sorry. This product clearly gives us our unit, and we are left with Rij of G and J psi of x. Now, since our psi is an arbitrary wave function, we can cancel out by psi and get the operator equality u dagger of j x I u of j is equal to r I j of g x j for any j of SO3. Now we can compare this equality with the general definition of the tensor operator. So we see that the rho of the matrix T is played here by the matrix of space rotation R. So, we get an irreducible tensor operator of SO3 that transforms according to the vector representation of SO3. And, in the same way, we can check the tensor properties of the operators E1 and MJ. Okay. Well, I see it's time to take a 5-minute break. So break. Okay, let us resume our lecture. We have introduced the notion of a tensor operator, which actually a set of operators as A with a specific transformation law with respect to some group G. And to any tensor operator, we can associate some representation T. And if this representation is happen to be irreducible, we speak about irreducible tensor operator. And as example, we can take the group G to be equal to the rotation group SO3, and for SO3 we have a plenty of different tensor operator, irreducible tensor operators, position coordinates, momentum, angular momentum. All these operators are irreducible tensor operators that are transform according to the vector or fundamental representation of the SO3 group. Now consider a pair of tensor operators S1 and S1A and S2A lowercase, SA capital and SA small. And suppose that the first tensor operator S1 transforms according to the representation T1, and S2 transforms according to some representation T2 of one and the same group G, right? Then we can multiply these operators, right? This is just operator, so you can multiply operators and get the operator as a capital A, which is given by the product as A1 and as A2. And the result is a new tensor operator which transforms according to the representation given by the tensor product of T1 and T2. T1 and T2. Right? If we apply unit transformation to this operator then and use the definition of the tensor operator, we find that this new operator transforms according to the tensor product of T1 and T2. So the set of 4 tensor operators is closed with respect to multiplication. It is also clear that any linear combinations of 2 tensor operators S1 and S2, which transform according to the same representation T, is again a tensor operator. Is again tensor operator for the representation T. The algebraic operations of addition and multiplication allows one to build a great number of new tensor operators starting with some given set of tensor operators. For instance, we can starting with their position coordinates and their conjugate momentar. We can construct a great number of new tensor operators for the group SO3. For example, xi, xj became triple product of operators x and p. Another example is the annihilation operator. We just take a linear combination of the irreducible operators x and p, which transforms according to the vector representation of SO3. One more example, M ij xi j minus xj pi angular momentum operators. Or let's take h given by p squared over to m is again it is a tensor operator. By the way, it follows from the definition of symmetry. That each Hamiltonian is a tensor operator which transforms according to the trivial representation of the symmetry group. So if G is a symmetry group of the operator H, then by definition of symmetry must equal to H, but this means that T of G is given by the unit. So we can think of each Hamiltonian as a tensor operator of the symmetry of its symmetry group are reducible. It is a reducible operator because here we have one-dimensional representation. One-dimensional representation is always irreducible, right? Please.
Here we define U as unitary transformation
Right.
that can serve the
You are unitary transformations, yeah.
and can we get from definition the last equation?
This is definition of symmetry.
Yes.
So here G is an arbitrary group.
Okay.
But now G is a symmetry group of H.
And then
And for symmetry group, we have another definition. So the group G is a symmetry group if the corresponding unitary transformations leave the Hamiltonian invariant. But comparing this equality, this definition of the tensor operator, we conclude that we can think about the Hamiltonian as a tensor operator associated with a trivial representation or unit representation of the symmetry group.
because Hamiltonian can take this Hamiltonian, for example.
Yes. Among the generators, this group has the Hamiltonian, but there may be some additional generators like the components of the angular momentum for the central potential and something else. Yeah. So here U is not just a evolution operator, maybe a big set of operators generating this generating symmetries of the Hamiltonian. Okay. Okay, let's, we are given by some group G that acts by unit transformations in the Hilbert space H of some quantum mechanical system. And in general, this unitary transformation with unitary representation is reducible. But since it is unitary, we can always decompose it. Okay, let me denote it T tilde. It's convenient to denote it tilde. But being unitary, it decomposes in the direct sum of irreducible representation. Let me label them T alpha. Label T alpha. So each T alpha acts in invariant subspace H alpha, so that the sum, the direct sum of all these subspaces H alpha gives me the full Hilbert space H. So we compose the space H into the direct sum of invariant subspaces for the representation T tilde, and T alpha is just the restriction of T tilde on the invariant subspace. Yeah. Okay. Then in each invariant subspace H alpha, I can choose some basis of states psi alpha I, where I runs from 1 to the dimension of the subspace H alpha. So taking union of all these bases, we get a basis in the space H. Consider now an irreducible tensor operator as A, which transforms according to some irreducible representation Tg, which acts in some finite dimensional vector space V. G from some group G. So, I have some symmetry group G. I have its unitary representation in the Hilbert space, and I take some tensor operator, or this reducible tensor operator, this symmetry group G. And consider now the matrix element Mij A. This is just a complex number, which is given by the inner product of psi I alpha S A psi beta J. So I take some basis vectors and make a sandwich with these vectors and the tensor operator SA. I give some matrix elements of these operators SA with respect to the chosen basis psi I alpha. And now we wish to know when this matrix element is equal to 0. This is the question.
Why this matrix element is equal to 0?
When, under which conditions, this matrix element is equal to 0. It is interesting to know that we can give a definite answer to this question just considering the properties of the reducible representation T alpha and T. So we can give answer in terms of properties, in group theoretical terms, in terms of the properties of reducible representation T alpha and T. To start with, let us write the formal equality which follows immediately from the definition of the tensor operator. I just apply these Bra and Ket vectors psi alpha, psi beta to this equality, to the both sides of this equality. What I get? Well, I get T R A B of G, scale product, inner product, psi alpha as B psi beta J, psi alpha I U dagger S U J psi G. And now I add by this operator U to the right and psi U dagger to the left and get, maybe I should write here the action of the operators T alpha of J in this basis psi alpha I. So since psi alpha form a basis in the invariant subspace, you get again a linear combination, some linear combination of these basis vectors, that is Ij psi alpha J. So now applying these operators U to the right and to the left, I get alpha and I of G T beta and G of G psi and alpha S A C M beta. Do you agree? And using this definition, how this operates on this representation T alpha and T beta act on the basis vector, we get this equality. So I see that this is nothing but my original matrix element M. So using with the help of the definition of the matrix element M, I can rewrite this equality in the following way. T alpha TAB MBIJ is equal to MA and M T star alpha and I to beta and J. As a scene are for fixed alpha and beta, for fixed representations, alpha and beta reducible representation, alpha and beta. These are matrix elements. These matrix elements define a rectangular matrix, of operator which acts from the tensor product of spaces H alpha star H beta to the space V, where the irreducible operator T tilde where representation T tilde operates. And this operator M intertwines the reducible representations T, reducible representation T with the tensor product of representations T beta and T alpha star. So it intertwines M intertwines representation T with T star alpha times T beta.
Here's a question.
Yeah, please.
We have a reducible set of Hamiltonians, and what is
what? We have an irreducible tensor operator S, no Hamiltonians. Okay.
Okay, I understand.
Please continue.
Yeah, no, I understand.
Okay. So let me somehow. We started with some irreducible tensor operator associated to represent irreducible representation T, right? Representation T. And we also have some irreducible operator T alpha corresponding to the action of our symmetry group in the vector space H. And from this equality we see that the matrix elements, various matrix elements of these tensor operators, they form a rectangular matrix of an operator that acts from the tensor product space to the space V, that this equality suggests. And this means that these are operator and it entwines the representation T with the representation in the tensor space, in the tensor product of spaces H alpha and H beta, which is given by these operators. In general, this tensor product representation is reducible, but again, we can always decompose it into reducible representations. dark product of irreducible representations. So that each irreducible representation Ti acts in some invariant subspace HA in H star alpha times H beta. In other words, this tensor product decomposes into the direct sum of invariant subspaces HA. So each TA of G acts in HA. And now we can restrict the operator M and the twining operator N onto each invariant subspace HA. We can consider the restriction of N onto invariant subspaces. These invariant subspaces. Let me denote MA, the restriction of M to the invariant subspace HA. So then this operator acts from HA to V. But HA is a space of an irreducible representation of the group G, as well as the space V. So each operator, the operator MA, intertwines irreducible representation TA with T. As we know from group theory, according to Schur's lemma, this operator MA, intertwining operator, may be different from zero only when the representation T and TA are equivalent. By Schur's lemma, are equivalent. But let us suppose now that none of these representations, irreducible representation TA in this expansion in the dark sum is equivalent to our representation T associated to the irreducible operator S. Then this means that each restriction is equal to 0. And this means that the operator M is 0 too. In other words, this matrix element is equal to 0 identically. Whenever these direct product decomposition doesn't contain our representation T. And we can use the above consideration to rederive the known selection rules for the electric dipole rotations. So selection rules for electric dipole transitions. Electric dipole transitions. Again, consider a charged scalar particle moving in its central force potential. As usual, we label the basis of stationary states by three quantum numbers: the principal number and the orbital number L and the magnetic number M. Now the components of the angular momentum, being constants of motion, integrals of motion, generate the dramatic action of the rotation group, SO3 group, in the Hilbert space of states of the particle. And as a result, this Hilbert space decomposes into the direct sum of invariant subspaces, invariant with respect to the action of SO3. And each eigenspace, each invariant subspace is tagged or labeled by two quantum numbers, N and L, principal quantum number and the orbital quantum number, so that subspace H and L is spanned by the vectors N, L, M, where M runs from minus L to L, so that dimension of NL is equal to 2L plus 1. Okay, and let me denote by TL the representation of the SO3 group corresponding to the value of the angular momentum L. The value of the angular momentum L. So the elements of this representation they act in the subspace NL. Okay. As you know, the operator of the electric dipole moment, has this form: minus E, where E is the charge, for example, of the electron, dx. D is some vector space. And we see that there are matrix elements of this operator, dipole moment operator. Various matrix elements are given by linear combinations of the matrix elements of the form NL, X, N prime, L prime, prime. So they are given by linear combination of the matrix elements of the irreducible tensor operator of the SO3 group. X is an irreducible tensor operator of SO3. So we wish to know when these matrix elements vanish. And these matrix elements vanish for which states, which basis states. This irreducible representation, this irreducible operator transforms according to the vector representation of the rotation group, right? Vector representation is just T1, right? T1, because for L equals 1, we have three-dimensional representation, three-dimensional space. this is a vector or fundamental representation of the symmetry group. Okay. Well, we know from group theory that the complex conjugate representation TL is actually equivalent to TL. Rotation group all its unitary representations are equivalent to the corresponding complex conjugate representations. Furthermore, the following decomposition for the tensor product takes place. Taking the tensor product of representation TL with some TL prime, we get a direct sum of representations T sub k, where k runs from L prime minus L to L prime plus L. So now we should decide whether this decomposition contains our representation T1 associated to the irreducible operator X, which matrix elements we consider. Under which condition this representation T1 may appear in this sum.
T1 is representation of generator X.
What?
Is representation.
T1, yeah, it is a representation associated with this irreducible tensor operator,
Okay.
X. Under which condition? K may take value 1 here. Do you see? Please?
If we have room, how let's say,
What?
we have как правило,
Selection rules.
selection rule.
Yeah.
Maybe we can part the selection rule of this.
We see that this sum starts with a difference, a 1 minus L. So we can find here Q1 only when this difference,
Plus minus 1.
yeah, is equal to, take values, either 0 or 1. Either 0 or 1. Furthermore, the matrix element in question also vanish when L is equal to L prime. So the case when the difference is 0 also leads to zero matrix element, and this can be seen as follows. The reason for that is that the symmetry group of the central potential, as we know, can be extended by the inversion, which acts in space by the rule x goes to minus x, inversion. So we can always extend the rotation group to a bigger group, O3, to the full orthogonal group, O3, by including this inversion in space. As a result, each stationary state in the coordinate representation is described by the wave function psi n L m of x, psi, which with a definite parity, that is psi n l m minus x is equal to minus 1 to L psi n L m of x. This is just the property of spherical functions, nothing else. So when we multiply two such functions for given number L, orbital number L, we get even functions. So the product psi star n L m x psi n prime L, observe here the same L. This function is even. So now consider the matrix element n L m x n prime L m prime. Let's given by this integral over space the x psi and this integral must vanish because this product is even under inversions, while this vector x changes sign. So by making coordinate change in this form, we get that this integral is equal to minus this integral, which means that it actually vanishes. Okay, how much time do I have? 5 minutes. So, okay. We write as a standard selection rules with respect to the orbital of azimuthal number. In order for these matrix elements, in order for these matrix elements of the electric dipole moment to be different from 0, the orbital numbers, the orbital quantum numbers, L prime and L of the initial and final states must differ by 1. The selection rule for the electric dipole interaction, electric dipole transitions. And similar arguments apply to the derivation of the selection rules with respect to the magnetic number. M. Let us restrict the full symmetry group SO3, rotation group SO3, to its axial subgroup SO2. We just restrict to subgroup SO2. This subgroup is generated by the third component of the angular momentum. Understand, this subgroup is generated by the third component. Then each basis vector, NLM spans an invariant subspace for the action of the rotation group SO2. Each element of SO2 is parameterized by the rotation angle phi. So applying rotation about the z axis to this basis vector, we act by this operator, and since this vector is an eigenvector for M3, we get immediately that this is equal to M5 and LM. And this eigenvalue of the operator U defines a representation of the group SO2 in a one-dimensional complex space spanned by this vector, by each basis vector. So actually I have a set of representations labeled by the integer number m. And since these representations are one-dimensional, they are all pairwise inequivalent to each other. They are different. What about the tensor products? If I take tensor product Tm star with Tm prime, since T is just a complex number, the tensor product reduces to the product of complex numbers. And multiplying the exponential function, I get, again, T, what I get?
Plus.
Minus. M prime minus M prime minus M. Because of the complex conjugation here. Now, the tensor operator X, the reducible tensor operator X, reducible for the full rotation group, becomes reducible with respect to the subgroup SO2. So instead of a single irreducible operator for SO3 group, I actually get three irreducible reducible operators for the group SO2. This is because the matrix of space rotations, cosine phi, sine phi, minus sine phi, cosine phi, 1, 1, 0, 0. This matrix can be brought into the diagonal form by a unitary transform. I can brought it to this form R I phi minus I phi 0, 0, 1. And instead of three-dimensional three-dimensional reducible representation of SO3, I have three one-dimensional representations of the group SO2. Let me introduce the following let me denote the corresponding eigenvectors of this matrix by V0, just 0, 0, 1, and V plus minus 1 plus minus E0. These are the eigenvalues of this diagonalized matrix. And by definition, the rotation through the angle phi, transform the vector V to V0 and R phi plus minus is given by plus minus I phi V plus minus. So instead of a single reducible operator X, I can define the following irreducible operators of the SO2 subgroup. V naught scalar product with X and X plus minus given by the scalar products of v plus minus with x plus minus I x2. And by definition, these are operators, x3, x plus, x minus, they transform according to some irreducible representation of the rotation group SO2. For example, if I apply rotation to x3, I get x3. It is quite clear because these rotations do not affect V naught. And for x plus x minus, I get plus minus I V x plus minus x. So this operator x3 transforms according to the representation T naught, trivial representation of unit representation of the rotation group where m is equal to v, and this T1 for plus and T minus 1 for minus. See this? Plus minus 1. Now it is clear that the tensor product of representations T star m with T m prime, which is given by T m prime in minus m, these tensor product may contain these representations, only when, so this representation may appear on the right hand side, only when m prime minus m is equal to or less, is given by 0 or plus minus 1. So in order to get here T1, T minus 1 to 0, this difference must be either 0 or plus minus 1. And this is nothing else but selection rules for the electric dipole transition with respect to the magnetic number. Okay, that's all for today. Do you have any questions? No questions. Okay, then let's finish our lecture.